Imagine a weapon launched from a truck parked in a forest clearing. Within seconds, a two-stage solid fuel rocket punches it into the upper atmosphere. Then something unusual happens. Instead of arcing high into space on a predictable ballistic curve, the kind that missile defense systems have spent decades learning to track, the rocket releases its payload. A compact wedge-shaped vehicle separates from the booster and drops into the atmosphere at speeds exceeding Mach 5. That is more than 1 mile every single second. But it does not fall like a stone. It glides. Using its aerodynamic shape and control surfaces, it rides the upper atmosphere on a flat maneuvering trajectory. It can turn, it can change altitude, it can shift its aim point hundreds of kilometers from its original course, and it does all of this while traveling so fast that the air around it superheats into a sheath of ionized plasma. This is a hypersonic boost glide weapon. And according to the Congressional Research Service, the key advantage of these weapons is not their speed. Ballistic missiles have traveled at hypersonic velocities for decades. The advantage is their ability to maneuver after release from the booster. A traditional ballistic warhead follows a fixed arc. Track the launch, calculate the curve, and you can predict where it lands. A hypersonic glide vehicle erases that prediction. Today we are opening up the engineering. How do you build a vehicle that survives 2,000 degrees? How does a scramjet burn fuel in an airflow moving faster than sound? There are two fundamentally different approaches to building a hypersonic weapon, and each one solves a different physics problem. The first is the boost glide vehicle. This is the design behind the US Army's Dark Eagle, Russia's Avangard, and China's DF-17. The concept is deceptively simple. Use a conventional rocket to carry a glide vehicle to the edge of space, accelerate it to extreme speed, and then release it. From that point on, the glide vehicle has no engine. It is unpowered. It flies entirely on aerodynamic lift, trading altitude for range as it descends through the upper atmosphere. Think of it as skipping a stone across water, except the stone is traveling at Mach 5 to Mach 17, and the water is the upper atmosphere. The vehicle enters the atmosphere, generates lift, and can pull back up into a shallower glide or execute lateral turns. This maneuvering is what separates it from a ballistic re-entry vehicle, which simply falls along a fixed arc. A glide vehicle's trajectory cannot be predicted from its launch point. You know where it was launched. You do not know where it is going. The second approach is the hypersonic cruise missile powered by an engine called a scramjet, short for supersonic combustion ramjet. A scramjet is an air-breathing engine with no moving parts, no turbines, no compressors. It relies entirely on the vehicle's own forward speed to ram air into the engine, compress it through carefully designed shockwaves, mix it with fuel, and ignite it, all while the airflow through the combustion chamber remains supersonic. That is the critical distinction. In a conventional ramjet, the incoming air is slowed to subsonic speeds before combustion. In a scramjet, the air stays supersonic the entire way through. This is what allows it to operate efficiently at Mach 5 and above. But there is a catch. A scramjet cannot generate thrust from a standstill. It only works once the vehicle is already moving at hypersonic speed. That means every scramjet-powered weapon needs a booster rocket to accelerate it to operating velocity before the scramjet can ignite. And because the fuel must be injected, mixed, and burned within milliseconds inside a supersonic airflow, the engineering tolerances are extraordinarily tight. Even the shape of the combustion chamber matters. Shockwaves must be managed precisely to maintain stable combustion. Russia's Zircon cruise missile, which has demonstrated speeds exceeding Mach 8 in tests, uses scramjet propulsion. The US Air Force's Hypersonic attack cruise missile is also scramjet-powered, with over $800 million requested for its development in fiscal year 2026. But the most mature weapons currently approaching deployment, Dark Eagle, Avangard, DF-17, are all boost glide vehicles. The scramjet remains the harder engineering problem. And then there is the biggest problem of all: heat. At Mach 10, the nose of a Dark Eagle reaches approximately 2,500 degrees Celsius, hot enough to melt through steel in seconds. When a vehicle travels through the atmosphere at Mach 5 or above, the air in front of it cannot move out of the way fast enough. It compresses violently, forming shock waves that convert kinetic energy into thermal energy. The temperatures at the vehicle's leading edges, the nose tip, the wing edges, any forward-facing surface, routinely exceed 2,000 degrees Celsius. That is well beyond the melting point of steel, beyond titanium, beyond most engineering metals. This is not just an engineering inconvenience, it is the central challenge of hypersonic weapon design. The vehicle must survive these temperatures while maintaining its aerodynamic shape, protecting its internal electronics and keeping its guidance systems operational. If the thermal protection fails, the vehicle disintegrates. The only thing standing between the weapon and destruction is a few millimeters of a specialized class of advanced ceramics called ultra-high temperature ceramics. These are based on borides, carbides, and nitrides of transition metals like zirconium, hafnium, and tantalum. Hafnium diboride and zirconium diboride, for example, maintain structural integrity at temperatures approaching 3000 degrees Celsius. They resist oxidation, thermal shock, and mechanical stress under conditions that would destroy conventional materials. But ceramics are brittle. A pure ceramic leading edge would crack under the rapid thermal cycling of hypersonic flight. So engineers reinforce them with carbon fibers or silicon carbide fibers, creating ceramic matrix composites that combine heat resistance with toughness. Some of the most advanced versions have even demonstrated a self-healing capability. When microcracks form under thermal stress, the material generates a protective oxide layer that seals the damage before it can spread. And there is another problem that heat creates. At hypersonic speeds, the air around the vehicle ionizes into plasma. This plasma sheath disrupts radio communications and can blind onboard sensors. A weapon hurtling toward its target at Mach 10 may be partially cut off from external guidance updates during portions of its flight. This is one reason why hypersonic glide vehicles require highly precise inertial navigation systems that can operate independently when satellite links are disrupted. A challenge that connects directly to the GPS vulnerabilities we examined in our last video. So when people talk about hypersonic weapons, the speed is only the beginning. The real story is the engineering stack required to make that speed useful. The booster that gets the vehicle moving fast enough, the shape that generates lift without tearing the weapon apart, the scramjet that only works once physics is already on your side, the materials that survive temperatures hot enough to destroy ordinary metals, and the guidance systems that keep functioning even when the air itself turns into plasma. These weapons are not just fast missiles, they are a solution to a chain of extreme physics problems, all happening at once, in real time, with almost no margin for error. And that's what makes them so dangerous. Once a vehicle can survive that environment, once it can maneuver inside that envelope, and once it can stay on course while everything around it is trying to melt, blind, or break it, you end up with a weapon that does not behave like the missile's defense systems were built to defeat. And that leads directly to the next question. What happens when the weapon works, but the defense still doesn't? That's where this story gets even more serious. Be sure to subscribe to get notified for our next video where we'll dive into the strategic problem created by hypersonic weapons. This is Null Inertia, the point where technology meets territory. Thanks for watching.